All right, LeChatelier's principle is an application of the Q versus K issue, that whenever you cause a change in an equilibrium system, by doing lots of different things, you can change the temperature, the pressure, the concentration. What the reaction has to react or shift to relieve that stress or that change that has been made. And that shift occurs because you're no longer at equilibrium, and so the reaction has to reestablish equilibrium in order to get Q back into numerical agreement with K. So when a change happens to an equilibrium system, the equilibrium will shift in order to bring Q back into numerical agreement with K. So let's use this reaction right here as an example. Don't worry about this part right here yet. That'll come up in our next video. Okay, if you add some reactant or product to the equilibrium mixture, let's say I add some NH3, or I add some hydrogen, or I take away some nitrogen. Okay, so if more reactant or product is added, we've increased what's called a common ion. These aren't really ions in this case, and we'll talk about common ions in the next part of Unit 6. Okay, when you add a reactant or a product, the reaction is going to shift to the opposite side of the chemical equation in order to use up that product or reactant that you've added. Okay, and what that means is it means basically something like this. And I don't think it's in, no, it's not in here. So let's say we have, here's our amount of NH3, and here's our amount of nitrogen, and here's our amount of oops, put it in the wrong spot. Our amount of hydrogen, okay? That's the amount we have at equilibrium. And now, all of a sudden, I'm going to add a bunch of NH3. That means the amount of NH3 is going to go up. Immediately, it's going to go up. So I added some more NH3. Okay, what the reaction's going to do is it's going to shift to the opposite side of the chemical equation of wherever you added it. So if I added some NH3, the reaction's going to shift this way. Okay, and I want you to think about mathematically why that happens. Think about the Q value, because remember, you're not at equilibrium. As soon as you add some more NH3, you're not at equilibrium anymore. So you've got the concentration of NH3 squared over the concentration of N2 over the concentration of H2 cubed. So if all of a sudden this number goes up, our Q value is much, much greater than K. So Q is greater than K. And again, with the way that's positioned, what does that mean? It means the reaction has to proceed to the left. So in this case, a lot of times they use the word shift. When you're talking about Q versus K, they use proceed. It means the same thing. Whether it's proceeding to the left or shifting to the left, it doesn't matter which word you use. It's the same thing. Okay, so when it shifts to the left, it's going to go this way, which means these are both going to go up. So what happens is the amount of N2 is going to increase. So basically something like that. And H2 is also going to increase until you reestablish equilibrium. So these both are going to go up, up, and up. And NH3, because it's shifting to the left, so we've added a bunch of NH3. Now the amount of NH3, as it starts to reestablish equilibrium, is going to go back down a little bit. Okay, and now at this point again, right there or so, we've now reestablished equilibrium. So N is high, or NH3 is still greater than it used to be. Okay, but so is nitrogen and so is hydrogen. Because when this happens, the equilibrium constant can't change. The concentration values will change, which means Q changes, but the equilibrium constant value can't change. You have to get it back into numerical agreement with the equilibrium constant. So N2 is going to go up, hydrogen is going to go up, and NH3 is still going to be higher than where it started at, but it's going to, from where that initial high is, it does have to drop back down. Okay, so in other words, the addition of a common ion, so when we added some NH3, and again, these aren't ions, I understand, but ions are going to come up later. What it does is it reduces the solubility of a substance. Okay, and that will come up later on, and we can use LeChatelier's principle to explain that. Okay, so when you add some product, the reaction is going to shift to the left-hand side to use up that added product in order to reestablish equilibrium. If you add some reactant, if I add some N2 or some H2, what's the reaction going to do? It's going to shift to the right-hand side. Again, to use up that added component. And again, to get Q, the way you can always explain these is to get Q back into numerical agreement with the equilibrium constant. Okay, and the same also applies. What if I take some hydrogen out of that container? What if I remove some hydrogen? Well, then the reaction is going to shift to make more of it. So therefore, it has to shift to the left-hand side so that the amount of H2 that you removed can be replaced, again, to get back into Q, back into numerical agreement with K. Okay, if I remove some ammonia, some NH3, if I take some of that out, the reaction is going to shift to the right. When it shifts to the right, it's going to make more NH3, again, to bring Q back into numerical agreement with K. And notice that when I took some hydrogen out, again, the reaction is going to shift to the left. That's going to make the amount of N2 go up. Of course it is. Anytime you shift to one side or the other, the side that you shift to makes the amount of on that side go up and on the other side go down. Okay? And again, we need to get back to those original ratios to make the Q value equal K. Okay, so let's look at a couple of examples of that. A student claims that if the amount of H2 is increased in the container, the amount of N2 in the container will also increase. Again, we're using the same reaction. N2 plus 3H2 makes 2 NH3s. So a student claims that if the amount of H2 is increased, so if we add some H2 in the container, the amount of N2 in the container will also increase. Agree or disagree, justify your answer. I am absolutely going to disagree with that comment because by adding hydrogen, that is going to cause the reaction to shift to the right. So reaction will shift to the right, which causes the amount of N2 to decrease. That's a perfectly acceptable answer there. Okay, example 2, if some NH3 is removed from the container, the mole fraction of N2 will increase, decrease, or remain the same. So again, if some NH, and when they say mole fraction, just think of moles. What about the moles of nitrogen? So if I remove some NH3 from this container, again, I have this, I'm going to take some out. What is the reaction going to do? It's going to shift to the right to make more NH3. And what's that going to do to the moles of nitrogen? Of course, when it shifts to the right, of course, the amount of nitrogen is going to go down. Okay, so therefore we're going to say decrease because reaction will shift to the right. And again, this is a great way to say it, to bring Q back into numerical agreement. And do you have to say that? No, clearly I didn't say that up here, but it is a good thing to say, absolutely. Numerical agreement with K. So when you remove some reactant or product, or when you add some reactant or product, Q, all of a sudden you're not at equilibrium anymore. So you have to figure out what's Q going to do. Q must do something to get back to the equilibrium constant, because when you remove a reactant or product, it will reestablish equilibrium with the same equilibrium constant, which means the ratio of the reactants and the products has to remain the same. So it will shift to the right or proceed to the right, or shift to the left or proceed to the left to bring Q back into numerical agreement with K, because again, the equilibrium constant value does not change. Okay, situation number 2. What happens if you change the volume of the container? Okay, if the volume of the container is increased, again, we saw this in a problem, in a question earlier, and I said you can use LeChatelier's principle to discuss this. Okay, so if the volume of the container is increased, what happens to the pressure? The pressure is going to go down. Okay? If the volume is decreased, so you make the container smaller, so volume is decreased, what happens? The pressure increases. Okay? And when that happens, the reaction has to shift to the side with fewer, not total particles, fewer gas particles. If the volume of the container is increased, the pressure is going to decrease, and it's going to shift. So the volume is increased, the pressure decreases, and then it shifts to the side with more gas particles. Again, similar to situation number 1, the value of the equilibrium constant doesn't change. So again, by changing the volume, the container has to reestablish equilibrium, and so the reaction is going to shift to the left or shift to the right, depending on which side has more or less gas particles. Okay, so let's go back to that question from yesterday, or from the previous video, right here. Okay, and so it said, using the example 6 from the previous section, the student transfers the equilibrium mixture to a container with a larger volume. So let's go back. Now we got to go back to example 6. So, which is right here. So the student transfers this equilibrium system to a container with a larger volume. So with a larger volume, you have a lower pressure. And with a lower pressure, it's going to shift to the side with more gas particles. Basically, there's more space, and so you can allow more gas particles to be in there. And so when you increase the volume, the reaction is going to shift to the side that has 2 gas particles, where over here you only have 1 gas particle. So when the volume goes down, the pressure goes up. And then you have less space, so it's going to shift to the side with fewer gas particles. When the volume goes up, the pressure goes down, and then it shifts to the side with more gas particles. What if the number of gas particles are the same on both sides? Then there's no shift that occurs when you change the volume of the container. Okay? All right, let's go back to that question then. It was down here. So, rewrite your answer using LeChatelier's principle rather than Q versus K. So, now I don't even remember what the question is. So, after we come in, would the mole fraction of VBO2 be less than, equal to, or greater than? So, we're going to say it's going to be less than, because, and it's always good when you use LeChatelier's principle to let the grader know you are talking about LeChatelier's principle. So I would say, because according to LeChatelier's principle, an increase in the volume causes a decrease in the pressure. Sorry, I forgot an S there. Which makes the reaction shift to the side with more gas particles. Okay? And that's all you would have to say there. Okay? You could talk about Q versus K there. We did that yesterday. But again, an easier way to answer that same question is using the LeChatelier's principle. The way we explained it with Q versus K, that was a tough way to explain it. Okay? Now, with gases, that absolutely is true. You make the volume bigger, the pressure goes down, it shifts to the side with fewer gas particles. How can this also apply with an aqueous solution? So instead of pressures, you have concentrations. Okay, in that case, think about what makes the solution bigger or smaller is the amount of water that's in it. If you add some water to a reaction mixture, it's like you're making the volume, which you are, you're making the volume of that container, which is water, bigger. And so when that happens, now the particles have more space. It's going to shift to the side with more aqueous particles. What happens if you let some of the water evaporate? Now the volume of your solution goes down. It's going to shift to the side with fewer aqueous particles. Okay, example 4 says, let's look at the question from last night's homework. So hopefully you did that, dealing with BA EDTA 2 minus. When more water is added to the solution, it's as if the volume of the solution is increased, which it really has. It's not as if it's increased, it has increased. And based on that situation we just discussed, when the volume of the container increases, so hopefully you're looking at that homework question from last night. Okay, it's question number 18 in your homework packet. Okay. It says the solution is diluted with distilled water to a total volume of 1 liter. After equilibrium has been reestablished, is the number of moles of Ba2 plus present in solution greater than, less than, or equal to the number of moles of Ba2 plus present in the original solution before it was diluted? So in that case, notice that in that reaction on number 18, you've got 2 aqueous particles on the left, and you've got 1 aqueous particle on the right. Okay, so when you dilute it and you add some water, you're increasing the volume of that solution, which means the reaction is going to shift to the side with more aqueous particles, which we can see is the reactant side, making the number of moles of Ba2 plus greater than it was in the original solution. So as this solution is diluted, the percent of Ba EDTA 2 minus that dissociates increases, causing the number of moles of Ba2 plus to increase. So whether it's a gas or whether it's an aqueous solution, when the volume increases, the pressure, when it's a gas, decreases, and it shifts to the side with more gas particles, or if it's water, with more aqueous particles. If the volume goes down, if it's a gas, the pressure goes up. If the volume goes down, you have to let some of the water evaporate. You can't take some stuff out. You can't take the water out because that's going to take some of the particles out too. You have to let the water evaporate. So if the water evaporates, the volume's gone down, and it's going to shift to the side with fewer gas particles if it's a gas, or fewer aqueous particles if it's an aqueous solution. Okay, now in both cases, example or situation 1 and situation 2, if you change the amount, if you remove some reactant or product, or if you add some reactant or product, or if you change the volume of the gas or the aqueous solution, the value of the equilibrium constant does not change. Okay, Q changes, and then Q has to go back into numerical agreement with the equilibrium constant. Okay, but by changing those things, by changing the volume, changing the amount of the reactants or the products, all you're doing is changing the Q value, which then has to work to get back into numerical agreement with the equilibrium constant. There's one more situation we're going to look at in the next video that does change the value of the equilibrium constant. And that's really important right now, that you recognize that when you change the volume or change the amount of the reactants or the products, the equilibrium constant value does not change. Q does, and then Q has to get back into agreement numerically with the equilibrium